All right, guys, so this is your help video for your review worksheet for this week. Once again, the problems I'm going to be going over are not the problems that are actually on your worksheet. Each problem is meant to be helpful for you, though. So like number 1 on here should be helpful for your number 1. And the reason I'm doing this is because the integration is something that we forget at this point in the year, and it's very important that you guys get sharp with that again. It's been a little while since we've done this, so it's very important you guys get sharp with it. It's a huge part of calculus, and we're about ready to start getting into a lot of integration topics, and we want you sharp on this stuff again. So instead of me just doing problems for you, I'm going to demonstrate problems and ask that you do them on your own worksheet. Okay, so without any further ado, let's get started. Let's do number 1. Right, so number 1 is the most basic integration question I can ask. It's the power rule. I should say reverse power rule, because we have a power rule for derivatives. This is kind of like the opposite of the derivative power rule. With derivatives, we multiply and subtract, but with integrals, we add and divide. So what do I mean by that? The integral of this would be add 1 to this power and then keep the coefficient, but divide by your new exponent. And we always put a plus c. And so the final answer here is going to be 4x to the 4th if you reduce plus c. Now, how do you know if you've done it right? You should be able to take the derivative, and that should take you right back to the original problem. If it doesn't, then something's wrong. Because what an integral is, it's the opposite of a derivative. So if you integrate, you can check your answer by differentiating it, and you should get back where you started. Right? So that's the power rule. That's the most basic integration thing that we've learned. This is more power rule stuff. It just doesn't look like it. So a lot of times when you have these radicals, what you're going to want to do is you're going to want to rewrite the problem. So for instance, I'm going to put 6/5 as just a fraction here in the front, and I'm going to change that 5th root of x into an x to the 1/5 power. That's what radicals are. Okay, so you can imagine there being a 1 right here. That's the numerator, and the root that we're taking is the denominator. So it's x to the 1/5. The 8 is fine the way that it is. All right, so now that I've rewritten it, now we can do our power rule. All right, so the power rule is you add 1 to the exponent. Now I gave you guys a shortcut a little while back for that. The way that you add the 1 to the exponents, you could do it the long way, which is just literally try to figure this out using basic math. But I don't prefer to go that way. I share with you guys a shortcut. And the shortcut is you add the bottom number to the top number. So that would be 6. And then you keep the denominator the same. So by adding the bottom and top number together, you get a new top number, 6, and then you keep the bottom number the same. And then we have 6/5 here. Now, after you add 1 to the power, you're supposed to divide by that power. So I'm going to divide by 6/5. But something else that we talked about is instead of dividing by the power, it's a lot easier to do something different here. Because my power is a fraction. So it's when you're dividing fractions, that's the same thing as multiplying the reciprocal. Right? Whenever we do like 2/3 divided by 5/7, don't we do same change flip? So dividing by a fraction is the same as multiplying by its reciprocal. So instead of dividing by 6/5, which you can do, I think it's just a lot easier to multiply by the reciprocal instead when you're dealing with fractions. Okay, so I'm gonna review all that. That's a lot that I just said. So let's start over, and then we'll move on. So step 1 is to rewrite the radical as a fraction power of 1/5. Step 2 is to add 1 to the power, which is top plus bottom, over the original bottom. Keep the coefficient. Instead of dividing by the power, we multiply by its reciprocal. Okay? Now the second part here, when you have a constant, the way you integrate that is you just put an x next to it. And once again, don't forget your plus c. So there's our power rule. And now we simplify, of course, if we can, and we definitely can. These cancel, and I'm left with x to the 6/5 minus 8x plus c. And this is called the antiderivative, by the way. It's the opposite of a derivative. It's the antiderivative. This is the derivative of this, but this is the derivative, antiderivative of that. All right? Number 3. All right, so once again, we're going to rewrite this. So I'm going to change this to a fraction standing all by itself, which you're allowed to do here. So that's one thing we'll do. Another thing, though, I want to do is I want to rewrite this. We don't like that. When you have a number on the top and an x to a power in the bottom, I can actually write the number with the x right next to it so long as I make its exponent a negative. That's just a rule about exponents. Another thing that I see that I can do here is this can be reduced. So that's what I'm going to do is I'm going to do negative 21 divided by 3, and I'm just going to make that negative 7, just so everything's as simple as possible. But of course you want to rewrite stuff first, okay? So then we're going to do our power rule. So we're going to add 1 to this power. Remember, that's top plus bottom over the original bottom. And instead of dividing by this power, I'm going to multiply by its reciprocal. For the next one, we're going to do minus 4, and we're going to add 1 to the power. Be careful there, that's a negative. So if you add 1 to it, it becomes a negative 1x. And then we're going to divide by that power. So I'm dividing by negative 1. And don't forget your plus c. So that's the power rule. And then, of course, you want to simplify again. So this 7 here is like a 7 over 1. And therefore, these are going to cancel. And you're left with 3 times negative 1, which is negative 3. And then this part's going to stay the same, x to the 7/3. Minus, well, I'm dividing 4 by a negative 1. So that 4 becomes a negative. But double negatives becomes a positive. So now that's going to be a positive 4. Also, x to the negative 1. Now I'm going to put it back on the bottom with a positive 1 power. The only reason I moved it to the top was so I could do the power rule. But after you've done the power rule, technically it's best to have it written in a simplified form where the term is in the denominator. And then finally we have our plus c. Okay? So there's the antiderivative for number 3. So the main thing I was trying to demonstrate for you guys on this problem was how to do this piece, which is to, first of all, move the term to the top, make the exponent negative, do your integration, and when you're done, move it back down to the bottom. All right, moving along. All right, so now we're going to start entering the world of U substitution. U substitution is a majorly important skill. It's used in almost every kind of integration problem there is. There's a few that don't use it, but man, it seems to be the thing. So you want to make sure you use it. What is U substitution? It's a way to simplify the expression so it's not so convoluted looking. Okay? Now, there's 2 ways to identify what your U is. There's the easy way. You're like, well, I'm always going to use it. Well, unfortunately, it doesn't always work, but The easy way is look for what's in parentheses. In other words, the inside function. I'll tell you what the harder way is in a second, but for now let's start with the easy way. So the easy way is to look for whatever's in parentheses, and that's your quote-unquote inside function. So in this case, that's my inside function. Step one is to write out u equals inside function. So in this case, u equals x cubed plus 5. Step two is to take the derivative of u with respect to x. So the derivative of u with respect to x is basically just going to be the derivative of this thing, which is 3x squared. Now we're doing derivatives, right? That's the opposite of an integral. So derivatives, which you guys are a little bit stronger with, is you move this, multiply that number to the front and take one away from it. It's the opposite of the power rule, right? For integration. This is the power rule for derivatives. They're opposites of each other. So that's the derivative. And the next thing you want to do is you want to solve for dx. In other words, get the dx by itself. So on this problem, if I were to multiply both sides by dx and divide both sides by this, I would end up with du over 3x squared equals dx. So now I've got dx by itself. Step 4 is to do the u substitution. So I'm going to replace this up here with u. So instead of x cubed plus 5 to the 5th power, now it's just u to the 5th power. You're going to keep anything else that's not the u. But we're also going to replace the dx. The dx, as we can see, is this. So I'm going to replace dx with du over 3x squared. And usually at this point, what's going to happen is we're going to be able to simplify and cancel. You usually will have no more x's after this next step. The 3x squareds here, they cancel each other out, and they leave us with, oops, it's not u squared, it's u to the 5th. Leaves us with that. After that, we integrate as usual. So now it's a simple power rule, where we add 1 to the power, divide by that number, and add c. And then we substitute back into the equation what u was in the first place. So we're going to back substitute. So what was u again? U was x cubed plus 5. So I'm going to write it like this. X cubed plus 5 to the 6th power over 6 plus c. Okay. Now technically what you could do is you could also write it like this. So on your paper, maybe write it both ways if you need to remember that. Instead of putting it over 6, that's the same thing as multiplying by 1/6, right? Because once again, dividing by a number is the same as multiplying by its reciprocal. It could be written in 2 different ways. But there's the answer. So, step 1, write down your u. How do you know what your u is? The easy way is just look for whatever's in parentheses. Step 2, find the derivative of that. Step 3, get the dx by itself. Step 4, replace everything with a u or a du that you can. Step 5, simplify. Step 6, integrate. Step 7, replace the u once again with what it originally was. Okay? Now, that's the easy way to find the u, which is really what you need. This really is the first step, is finding the u is step 1. The easy way is looking for what's in parentheses. What's the harder way? The harder way is, do you see an expression multiplied by its derivative? Now this is a more powerful way, but it's a little bit more tricky. because it requires you to be able to do derivatives in your head. So do you see an expression that's being multiplied by its derivative? Like right here, for instance, I see an expression, and what's the derivative of that? Well, you have to be able to do that in your head. The derivative of that is 3x squared. So do you see an expression that's being multiplied by its derivative? Yes, we do. So therefore, that expression that we looked at in the beginning is therefore the u. Now, a lot of times it's the thing that's in parentheses, so that's why that's the easy approach. But it's not always. So do you see an expression, and I shouldn't say this being multiplied by, because it actually could be something else, by the way. But do you see an expression and its derivative somewhere in the problem? A lot of times it is multiplying, but it could be something else. So do you see an expression and its derivative? If you do, then that expression that you see is probably the u. So that's your basic u substitution problem, a very useful and necessary integration skill. Make sure you know how to master that for sure. Okay, so moving on to number 5, we have another u sub problem here. Once again, the easy approach to recognize your u is to realize it's the number that's in parentheses, usually. The other way to tell your u is if you take the derivative of this, which we have to do anyway, so I'll do that right now. If you take the derivative of that, do you see that number somewhere in your problem? It's there. I know that says 24 and it doesn't say 12, but it doesn't matter because isn't that just 12 times 2? So there is a 12x squared in there. In other words, it doesn't have to be exactly the same, but so long as it has the same number and power, you're good to go. So after you, step 1, identify your u. Step 2, find the derivative. Step 3, get the dx by itself. So once again, you multiply both sides by dx and divide both sides by 12x squared to get the dx by itself, and you're going to get that. Next, we go ahead and we do our u substitution. We're going to leave the top the same. We're going to replace 4x cubed plus 3 with u. And we're going to replace dx with what dx is equal to, which is du over 12x squared. And then we simplify. So 12 divides into 24 twice. And then this x squared and this x squared cancel. And so now I'm left with a much simpler looking expression, which is the whole purpose of u substitution. All right. And now we get to remember how to integrate these, which we talked about, I think, on number 3 of this worksheet. We want to move that variable up to the numerator with the 2, and in so doing, change the power to a negative. And then we could apply the power rule to this. So we add 1 to the power. Now be careful, that's a negative, so if you add 1, you actually get a negative 2. And then you're going to divide by that number. And don't forget your plus c. So in this case, 2 goes into 2 once, but it is negative, so we're actually having a negative as a result. So negative u to the negative 2. And then also, we don't like to leave the u with a negative exponent, so what we'll do is we'll rewrite it as a fraction. And there's our final answer for that one. Actually, you know what? That's not our final answer. I forgot the last step. The last step is to replace the u with what u equals. U equaled 4x cubed plus 3. That's my final answer. All right. Moving on. Let's do number 6. So now we kind of get it to go into the joy of trigonometric integrals. So it'll be helpful for you to review your derivatives of trig functions and the integrals of trig functions. So I'll write that as a note here. Review 2 things. Integrals of trig functions and derivatives of trigs. As you've noticed, whenever you're doing integrals, sometimes you have to do derivatives also because of the u substitution process. So, and that's what we're going to have to do here. So make sure you know your derivatives of all your trig functions and your derivatives of your integrals of trig function. I'm sorry, your integral of trig functions really well to do these. So without any further ado, let's get started on the problem. Step 1 is to identify the u. The u is the cosecant of 2x. And then 2, we want to take the derivative of that. And now you can see why I was saying you want to know your derivatives of trig functions when you're doing integration. So the derivative of cosecant is negative cosecant and cotangent multiplied together. And what goes in parentheses here is the same thing that's up here. So I'm just going to put the 2x in there. But we actually have a chain rule here. What I just wrote is the derivative of the outside, but we do need to multiply by the derivative of the inside. So I'm going to put a 2 in the front also. And then, so that was a little bit trickier, right? Doing your derivatives of a trig function there. Now we want to move on to step 3, getting that dx by itself. So once again, you're just going to multiply both sides by dx and divide both sides by this whole thing. And when you do that, you end up with this expression. And now we're ready for our u substitution step. All right. So I'm going to replace this with a u. And I'm going to replace this with that whole thing. And then all this is just going to stay there for now. Oops. The order doesn't really matter, but I'll just make it look like what it says there. And as you guys can see, the cotangent will cancel the cotangent. The cosecant is going to cancel the cosecant. The negative 2 is going to cancel the negative 4 and do a 2. And so now I'm left with something much simpler looking. And that's the beauty of u substitution. It takes something that makes something look like a nightmare and it turns it into something so much simpler to look at. All right. So now what? Now we integrate, right? So we add 1 to our power. So you add the top number to the bottom number to get 4, and you keep the denominator the same, 3. So that's going to be my new power. And then you would divide by that number, but when it's a fraction, instead of dividing by the fraction, we said it's best to multiply by its reciprocal. It's much easier. And don't forget your plus c. All right, now the 2 over 1, the 2 and the 4 can be reduced there, right? The 2 goes away and the 4 becomes 2. So you're left with the following result. We have 3/2 u to the 4/3 plus c. And we want to replace the u with what u equals, which we said in the beginning was cosecant of 2x. And there you go. It's number 6. So trigs. So in preparation for your review test on derivatives, I would go back to Unit 1 and Unit 2 and find those parts of your notes that have the tables where I gave you all the integrals and derivatives of trig functions. That'll be a nice little piece of notes to keep handy while you're doing your review test on integrals that'll be coming up soon. All right, now these problems are what I like to call the extra work problems. And the reason they're extra work is because we're still going to do u substitution, but after we do our u substitution, we're going to realize, oh darn, there's still an x there, and that happens. That does happen. So we'll talk about how to deal with that. So let's go ahead and just proceed forth blindly, and then we'll run into the problem as we go. So once again, you start with the part that's inside the parentheses. you find the derivative of that, you get the dx by itself. You do your u substitution. All right, fair enough. But we have a little bit of an issue here. We have an x still. The x isn't going to cancel out. Now I could rewrite this a little bit right now just to make it look a little bit nicer, I guess. I'm going to leave the x here. I'm going to put the 5 and the 3 together, the 5 on top and the 3 on the bottom. And I'm also going to change the u into a half power. So that those will all be helpful things to do. But really right now we still have a problem. That x should not be there. So we run into our issue that I told you we were going to experience here. Sometimes that happens. So what do we do about this? We can't have any x in there. We got to get rid of it somehow. So what we do is we go back here and we solve for x. So let me show you what I mean by that. So I'm going to take my u equals 3x minus 1, and I'm going to solve for x. So I'm going to add 1 on both sides first, and then I'm going to divide both sides by 3. And it's easier if you write them as separate fractions, by the way. I've found that to be true for these problems myself. And now what we do is, since x equals this, I'm going to put that right in there instead of the x. So now I won't have an x anymore. I'll just have a new thing with a u in it. I'm just going to leave that u in the top, actually, u to the half. All right, so I'm going to replace x with u over 3 plus 1 over 3. And now what we're going to do is we're going to take this fraction here and we're going to distribute it into the parentheses. All right, so 5, let's do this times this first. So the 5 is going to stay there. And then u to the first power times u to the half, you would have to add those together. So what is 1 plus a half? That would be 3 halves. And on the bottom, 3 times 3 is 9. So that's that one. Now I'm going to distribute the fraction into the 1/3 now. So the 1 times the top means the top's just going to stay the same. So it's just going to be 5u to the half power. The bottom, 3 times 3 is going to be 9. And then, of course, you want to rewrite and simplify. So I'm going to rewrite it a little bit like this. I'm going to put 5/9 u to the 3 halves plus 5/9 u to the 1/2 du. And now we can just integrate using the power rule. So that's the idea there. So let's review before we go any further. When you have an x left over, what do? You go back to the u, you solve for x, and you plug that in, and you simplify. You'll notice I did a few things, though, to make this process streamlined a little bit better. I put the coefficients together as a common fraction. I rewrote my square root as an exponent, and then I distributed it into the parentheses. So I've just found that those are good ways to write the problem out so that there's less confusion if you start that way by grouping the coefficients and getting everything in exponential form. Much easier when it comes to the distribution process. All right, so continuing. So now we're going to integrate. So we add 1 to the power, which means you do top plus bottom. Keep the bottom the same. And then we multiply by the reciprocal of that number, which is 2/5. Plus, repeat here for this one as well. We're going to add 1 to the exponent. And then we multiply by the reciprocal. Don't forget your plus c. Simplify. And then last step is to replace the u with what u equals. And we said in the beginning that u is 3x plus 1. And there you go. So sometimes you have an x left over. So what do? Go back to the u, solve for x, and do another substitution. Okay? Let's continue onwards. All right, got ourselves a trig integral going on here. So, once again, step 1, what's my u? My u is going to be 5x to the 5th plus 5. Step 2, find your derivative. Step 3, get that dx by itself. Step 4, do your u substitution. This is going to stay, but this gets replaced with u, and this gets replaced with du over 25x to the 4th. Step 1, 2, 3, 4, 5. We reduce or cancel or simplify, so the x to the 4ths go away, and 25 goes into 50 twice. So we're left with a negative 2 there in the front. And for trig integrals, when you're doing a trig integration, anything that doesn't belong there, we want to get rid of it. So since that's a constant multiplier, you can just pull it out. Remember, you can only do that for things that are multiplying. You can't do it for things that are adding. But there's that. Now you would have to go back to your notes if you don't remember. But this is on one of those charts I told you for trig rules for integration you want to know. There's a very simple and direct answer for that. The integral of secant squared is tangent. So we end up with negative 2, because that negative 2 is in the front, tangent of u. And you just put a plus c. Last step is, of course, though, we don't want to forget to replace that u with what u equals. And u was 5x to the 5th plus 3. Okay, so that's our final answer there. So make sure you have, once again, when you guys take your test on the review, which will be coming up after our Unit 6 test, we'll have the review test on these integrals. Make sure you have those notes printed on all the common integrals and derivatives for trig functions if you don't have them memorized very well. All right. Let's go ahead and do this next one here. Something I wish that they would do here just to kind of help students not be so confused is I wish they'd put parentheses around these ln problems like this. It'd be a lot more helpful. But anyway, so all right, so now we're kind of getting into what's our u going to be? What's our u going to be? It's kind of hard to tell on this one. Well, if you make this your u, all you're going to end up with is negative 1, and that's not going to cancel anything out. The whole point of doing u substitution is so that after you do all your substitutions, it cancels out things. So that's not going to cancel anything out if I do that. So that's not my u. Now, a really tempting thing would be to make this your u, because as you guys might recall, the derivative of ln is 1 over x. So in this case, it'll be negative 1 over negative x, which is still 1 over x. But 1 over x, well, here's an x on the bottom. So that's kind of like a 1 over x, isn't it? So that's close. But guess what? The u on this one is actually going to be this whole thing. So yes, it is going to include this, but I want to include the 4. Why? Because when you take the derivative of a constant, it just goes away. And the more stuff you can get rid of in the process of doing u substitution, the better. So that whole set there in parentheses is going to be my u. So u equals negative 4 plus ln of negative x. So let's do our derivative here. The derivative of 4 goes away because derivative of a constant is 0. Now, ln. This is a chain rule. We have the derivative of the outside, and then we have the derivative of the inside. When you're doing the derivative of natural log, it's going to be the derivative of the outside is 1 over and whatever the inside is. That's how you do the derivative of log. But we also want to multiply that by the derivative of the inside, which is -1. And these negatives cancel, so ultimately we're just left with 1 over x. So now, solving for dx is a little bit different this time. If you multiply both sides by dx, you end up with this. And then if you multiply both sides by x, you end up with this. So our outcome for solving for dx looks a little different this time, so be careful. All right. So now we're ready to rewrite this. The 4 cosecant squared all stays the same, but I am going to replace everything in parentheses there with a u. The x is going to stay there, and then I'm going to replace the dx with x du. And the beautiful thing about that is that the x's cancel out. We have another constant multiple, so I'm going to pull that out of the brackets there. And now we're looking at a very simple and basic integration rule. The integral, if you look at your notes from the integration rules for trigonometric functions, the integral of cosecant squared is negative cotangent. I put it in parentheses because I don't want you to think it's 4 minus cotangent. It's not. It's 4 times negative cotangent. So it's actually going to be -4 cotangent of u. And then my u, as we said earlier, was this really weird looking expression here. And now we're good to go. All right. Next one, more trig integration. All right, so a lot like number 9, they're failing to do something that I think would be very helpful to make this look a little bit less confusing. So what we have here is we've got 15 times cosine of -3x being multiplied by cosine of sine of -3x. So I really wish they put parentheses around that. Otherwise, it looks like it's cosine minus something, and it's not. There's a way you can know that because you can't subtract something from just cosine. Cosine has to have a number plugged into it, but still, it's very confusing looking to our minds the way that we see things. So it's an unfortunate way to write it. But so I'll add those parentheses, and hopefully that'll make things a little bit clearer. But let's go ahead and begin our process here. So step 1, what is my u? Well, if I just made it the -3x, that's not going to cancel enough stuff out. But hold on a second. Okay, I had to step away for a minute, so I'm a little lost on where I was, so let me review. So we were looking for our u. We said it wasn't going to be the -3x. So it's going to be the other one in parentheses there. It's going to be the sine of -3x. Let's go ahead and give it a shot there. So the derivative of sine is cosine. Once again, you'd have to have those reference sheets out if you don't know that. And the derivative of the inside, which is -3x, the derivative of that is -3, so we'll put that there. And then once again, we want to get that dx by itself, so this is what would happen if you attempted to do that. And then we go ahead and do our u substitution. So I'm going to replace this with a u. I'm going to replace that with the du over -3 cosine of -3x. And then everything else is just going to stay there. All right, so the cosine 3x's go away, and the -3 goes into the 15 -5 times, thus leaving us with a much simpler looking expression. And we like to take these constant multipliers out like that. And then we look at our reference sheet for trigonometric integration, and we see that that has a very simple answer to it. The answer is sine plus c. And we want to replace the u with what sine originally was, which was this. So we have that is our final answer. All right, and that does it for our integration review for this week. More to come next week. Hope you guys are taking this opportunity to really master those integrals. Super important. See you guys next time.